All right. Welcome back, honors chemistry people. We are now going to start talking about stoichiometry. Now, stoichiometry sounds really scary, and in reality, it's one of my favorite parts of chemistry because this is math. This is where the math of the balanced equation helps you understand what's happening in a reaction. Now, stoichiometry is a word that comes from German, an old German verb that actually means to measure, which comes from an old Greek word. So basically, what we're doing today is we're using the mathematics of a balanced chemical equation and knowing moles and the ratio of moles from that balanced equation so that we can go from grams to moles like we have done, but not only of the things that we know, but maybe something that we want to know about in relationship to something else in a balanced chemical reaction. So stoichiometry is the study of quantitative, meaning numbers. We can actually measure relationships between the amounts of reactants that we may need and the amounts of products formed by a chemical reaction. It's called stoichiometry. Stoichiometry is based on Antoine Lavoisier's law of conservation of mass. Okay, recall that the law states that matter is neither created nor destroyed in a chemical reaction. Okay, so what is in a reaction is what's going to come out. It may be bonded differently and it may be different things, but the mass going into a reaction is always going to be the mass coming out of a reaction. Okay, so in any chemical reaction, the amount of matter present at the end of the reaction is the same that we start with. Okay, therefore, the mass of reactants has to equal the mass of the products. So the very first thing we ever do when we start with stoichiometry is to balance the chemical equation. That's the very first thing that we've got to do. Always, always balance the chemical equation. So, first thing, balance the chemical equation. Okay, that's the very first thing to do. Now, if you're given a full chemical equation, that's a skeleton, balance it. If you're just given the reactants, then what you have to do is figure out what the products will be. And then once you've got the skeleton down, then go back and balance it. Remember, make sure that you've got the reactants and the products down first before you go and balance the equation. So let's start with example 1. Let's balance this equation. Okay, so I've got 1 iron here. I've got 2 here. So I'm going to put a 2 right here. And I've got 2 oxygens here, and I've got 3 here. So I need to look at my least common multiple between 2 and 3, which happens to be 6. So I'm going to need to make 3 O2s to give me 6 oxygens, and I'm going to need to make 2 iron 3 oxides to give me 6 oxygens, which means that I need to go back and I've got to change my coefficient in front of my iron. Okay, so here are my balanced equations. Now my question is, what do those coefficients in that balanced equation represent? Think about it for a minute. Why do we put these numbers in here? Do you have any ideas? Hopefully you said that it gives us a ratio between the compounds. It could give us a mole ratio. It could give us a particle ratio. It could even give us an atom ratio. All of these things are correct, but those coefficients determine the ratio of how much we have to how much of another thing that we have within a chemical reaction. It's kind of like a recipe. Have you ever followed a recipe? When we're measuring cups and teaspoons and whatever, that is a ratio of how much of things we have in the reaction. Cooking is reactions. Okay, so we are now going to layer in these ratios from the balanced chemical equation that the coefficients give us with unit analysis. Remember doing unit analysis at the beginning of the year? This is where it all comes together. Okay, so What if I had 4 moles of iron and unlimited oxygen? How much iron 3 oxide could I make? Could I produce? So what I'm going to do is I'm going to start with what I know. I know I've got 4 moles of iron. So 4 moles, oh wow. So 4 moles of iron. And now what I have to do is I need to look at my balanced chemical equation. And we are going to compare the two coefficients of the things that we want to compare. We want to compare iron and iron 3 oxide. So I am going to grab the coefficients from iron, which is 4 moles of iron, to 2 moles of iron 3 oxide. I'm going to grab those coefficients. Now I'm going to use unit analysis. And in using unit analysis, I have moles of iron. I want to cancel out my moles of iron, don't I? And I want to get into moles of iron 3 oxide. So since I have 4 moles of iron on the top, I need to put my moles of iron for my balanced chemical equation on the bottom to cancel it out. So this 4 moles of iron is going to go here. I have 4 moles of iron reacting to make me 2 moles of iron 3 oxide. Okay, so the mathematics is the same. 4 times 2 is 8, divided by 4 is 2, right? So this will give me 2 moles of iron 3 oxide. Okay, so notice we grabbed the mole ratio of 4 moles of iron to 2 moles of iron 3 oxide. So let's do another example. We're going to always grab the coefficients straight from the balanced equation. So here we go. Here's another example. I have 6 moles of oxygen and unlimited iron. How much iron 3 oxide could I make? So once again, I'm going to start with what I know. I know that I have 6 moles of oxygen. Okay, so let's grab that balanced equation. I want to compare oxygen with iron 3 oxide. So I know that I have 3 moles of oxygen to 2 moles of iron 3 oxide. So we're going to use that mole ratio. I have 3 moles of oxygen to 2 moles of iron 3 oxide. Now, using the unit analysis, I want to cancel out my moles of oxygen, which means on the next step that oxygen has to be on the opposite side. So it's going to have to be on the bottom. So I'm going to take this 3 moles of oxygen and I'm going to put it on the bottom. For 3 moles of oxygen, I'm able to create 2 moles of iron 3 oxide. Okay, my moles of oxygen cancel, and I have moles of iron 3 oxide. Just what I wanted to know. I wanted to know that. How much iron 3 oxide? Okay, so let's do the math. 6 times 2 is 12, divided by 3 is 4. So I will be able to make 4 moles of iron 3 oxide. Okay, now hopefully this will let me write. Okay, 4 moles of iron 3 oxide. Okay, so hopefully the important and obvious point of these examples is that the coefficients in a balanced equation tell us the mole ratio. So the coefficients in the balanced equation tell us the mole ratio. Okay, and we are going to use the mole ratio from balanced equations over and over and over again to do this. This is the concept in stoichiometry. This is what we're doing. We're taking balanced equations, we're using the coefficients from those mole ratios to do the math behind the law of conservation of mass. Okay, so let's try 2 more related above. How many moles of iron would be required to react completely with 6 moles of oxygen. So once again, I'm going to start with my moles of oxygen. I'm going to start with what I know. And this time, we're not going to be even looking at iron trioxide. We're going to be comparing oxygen with iron. Okay? So if I have 6 moles of oxygen, we're going to be looking at oxygen here and iron. So if I look at oxygen, I have 3 moles of oxygen to 4 moles of iron. Okay, so that's what we're going to use. Now, my moles of oxygen I want to cancel, so it needs to be on the opposite side. So 3 moles of oxygen react with 4 moles of iron. Okay, so that is the mole ratio that we got from the balanced equation. Okay, remember, this comes from the balanced equation. From equation. Okay, now my moles of oxygen cancel out, and I'm left with moles of iron, which is what I wanted to know. I want to know how many moles of iron. Okay, so let's do the math. 6 times 4 is 24, divided by 3 would give me 8 moles of iron. Oops, I can't write today. So I would be dealing with 8 moles of iron here. So let's do this next one. How many moles of iron and oxygen would be required to produce 8 moles of iron trioxide? So I'm going to start with what I know. I want to make 8 moles of iron trioxide, and I want to know how much iron, let's do iron first, that I need to have. So in my balanced equation, I have 2 moles of iron trioxide reacting with 4 moles of iron. So I'm going to use that ratio here. So I have 2 moles of iron trioxide reacting with 4 moles of iron. My moles of iron trioxide cancel. I'm left with moles of iron, which is what I wanted to know. So 8 times 4 is 32, divided by 2 gives me 16 moles of iron is what I'm going to need to start with. Let's look at oxygen. Now I still want to make the 8 moles of iron trioxide. Now we're going to see how much oxygen we've got to start off with. So back to our balanced equation. What's the ratio? So we have 3 moles of oxygen to 2 moles of iron trioxide. So we're going to use that ratio. So 2 moles of iron trioxide will react from 3 moles of oxygen. My moles of iron trioxide cancel out. Let's do the math. 8 times 3 is 24, divided by 2 is 12. So I will need to start out with 12 moles of oxygen. Okay, so hopefully this is making sense that I am grabbing the coefficients from the balanced equation to create a ratio in these equations. Okay, example 2. If I have 4.83 moles of bromine and I react it with excess sodium, how many moles of sodium bromide will be formed according to the equation below? Remember, the first step is to always balance the equation. I will almost always give you just a skeleton equation. And because it's a skeleton equation, that means it's not balanced. That means you need to check it and make sure it's balanced. So let's balance this. Okay, I've got 1 sodium, 1 sodium. I'm okay. 2 bromines, 1 bromine. So I need to double this, which means I need to double that. Okay? Now, once the equation is balanced, now I have that ratio that I can use. So we are going to convert the moles of the given substance. What is the given substance here? I know that I have 4.83 moles of bromine. So that's what we're going to start off with. So I have 4.83 moles of bromine. And now remember, bromine is diatomic, right? And I want to know about what? I want to know about moles of sodium bromide. So I'm going to grab the ratio. So bromine and sodium bromide are the ratios I'm going to grab. So how many moles of bromine do I have? Remember, if there is not a coefficient listed, that coefficient of 1 is assumed. Okay? So I have 1 mole of bromine reacting to produce 2 moles of sodium bromide. Okay, my moles of bromine cancel out. I'm now into moles of sodium bromide, which is what I wanted to know about. Now I'm going to do the math. 4.83 times 2 divided by 1. Let's see, 4.83, 9.66. So this will give me 9.66 moles of sodium bromide. That can be produced off of the 4.83 moles of bromine. Okay, notice how we're using balanced equations and unit analysis and our relationship with moles all together. Okay, do you think because we can do moles to grams that we could do that in stoichiometry as well? Do you think? That's what we do in the lab because I don't measure moles in the lab. I don't have a balance that can measure moles, but I sure have a balance that can measure grams. So that's what we do in the lab. We take moles, we convert it into grams, and then we use this mole ratio, and then we figure out how many grams of something else that we need to either match with it to make what we want, or how many moles or grams of something that we'll produce in the reaction. So here we go. Let's do some more math here. Example 3, if I have 96 grams of oxygen, notice oxygen is diatomic. Remember our diatomic elements, Brinkelhoff. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are diatomic. So you need to remember that when they are elemental, meaning that they are by themselves, they pair up with another atom of the same element. Okay? So if I have 96 grams of oxygen and it's reacting with excess carbon monoxide, how many moles of carbon dioxide will be formed? First thing first, we've got to come up with an equation. Okay? So I am reacting oxygen with carbon monoxide, and I'm creating carbon dioxide. Okay, there's my skeleton. Now, what do I need to do once I've got my skeleton down? I've got to go and balance it, right? So I've got 3 oxygens and 2 here. Let's try this. Let's double this. That now gives me 4 oxygens and 2 carbons. So if I double that, we've got 2 carbons, 4 oxygens on both sides. So we're good. Okay? Now the next step then is to start off with what I know. I know I have 96 grams of oxygen. And I want to compare oxygen with carbon dioxide. So the first thing to do is to convert grams of the oxygen that I know into moles of oxygen. So I've got 96, and now it wants to think. Hopefully it won't take too long for it to think. Oh, wow. That was quite a long time. Okay, so I'm going to take the 96, and it's still thinking. Yay. I'm going to take the 96 grams, or 96.0. I need to have the same sig figs there. 96.0 grams of oxygen. How many grams of oxygen are in 1 mole of oxygen? Now, I'm sure a lot of you are like, yeah, 16. That was when we were just doing single oxygen atoms. This is diatomic elemental oxygen. So how many grams really are there? 16 times 2 is 32. So there's 32 grams of oxygen in 1 mole of oxygen. Okay? So my grams of oxygen cancel out, and I now have moles of oxygen. So 96 divided by 32 will give me 3 moles of oxygen. Okay? Now remember, we are going to do sig figs here. So be careful with that. Okay? Now, the next step is we've got to convert the moles of the given substance into the moles of the unknown substance. Okay? And the unknown is carbon dioxide. That's what we want to know. So we're going to grab our ratio in the equation. We're going to grab our oxygen, which is 1 mole here, and we're going to grab our coefficient of carbon dioxide, which is 2. Okay? So we're going to start with the 3 moles that we were able to calculate before. We have 3 moles of oxygen, and we're going to use our ratio from that balanced equation. We have 1 mole of oxygen reacting to make 2 moles of carbon dioxide. Okay, so my moles of oxygen cancel, and I now have moles of carbon dioxide, which is what I want to know. Okay, so 3 times 2 is 6 divided by 1 gives me 6 moles of carbon dioxide is what I'm going to be able to produce. Now, do you think we can string all of that together in just one big expression? We sure can, and it makes it a lot easier if we do it that way. So let's string that together. Okay, so I've got the 96. Oh boy, that color change came pretty late, didn't it? I've got 96 grams of oxygen. And in 1 mole of oxygen, I've got to get it into moles, I have 32 grams of oxygen. Okay, so that was this first step right here. Now, my grams of oxygen canceled out, but I don't want moles of oxygen. I want moles of carbon dioxide. So I'm going to grab the coefficients from the equation. So I have 1 mole of oxygen. That will cancel out my moles of oxygen to 2 moles of carbon dioxide. So I'm left with moles of carbon dioxide, which is exactly what I was asking about. How many moles of carbon dioxide will be formed, right? That is what I wanted to know right here. Okay, so same math here. 96 divided by 32 is 3 times 2 is 6. So 6 moles of carbon dioxide is what I can make. All right, now, do you think we can do the whole thing where we go from grams to moles of the unknown stuff, then back to grams of the unknown stuff? We sure can, and that is what stoichiometry is all about. So, what mass of oxygen is required to react with 100 grams of iron to produce iron 3 oxide? Okay, so first thing we've got to do is write a balanced equation. So here we go. We have iron. Is this going to let me write? We have iron. Why isn't this letting me write? All right.